Most of these formulas should be memorized. It is useful to know them all, but the ones marked with an asterisk need not be memorized since they are easily derived. Formula 19 can be avoided by using partial fractions, and trigonometric substitutions can be used in place of Formula 20. Once you are armed with these basic integration formulas, if you don't immediately see how to attack a given integral, you might try the following four-step strategy. Number one, simplify the integrand if possible. Sometimes the use of algebraic manipulation or trigonometric identities will simplify the integrand and make the method of integration obvious. Here are some examples. The integral of the square root of x open 1 plus the square root of x closed dx equals the integral of open square root of x plus x closed dx. The integral of tangent theta over secant squared theta d theta equals sine equals the integral of sine theta over cosine theta times cosine squared theta d theta equals the integral of sine theta cosine theta d theta equals 1/2 the integral of sine 2 theta d theta. The integral of open sine x plus cosine x closed squared dx equals the integral of open sine squared x plus 2 sine x cosine x plus cosine squared x closed dx equals the integral of open 1 plus 2 sine x cosine x closed dx. Number 2, look for an obvious substitution. Try to find some function u equals g of x for the integrand whose differential du equals g prime of x dx also occurs apart from a constant factor. For instance, in the integral of x over x squared minus 1 dx, we notice that if u equals x squared minus 1, then du equals 2x dx. Therefore, we use the substitution u equals x squared minus 1 instead of the method of partial fractions. Part 3, number 3, classify the integrand according to its form. If steps 1 and 2 have not led to the solution, then we take a look at the form of the integrand f of x. A. Trigonometric functions. If f of x is a product of powers and sine x and cosine x of tangent x and secant x, or of cotangent x and cosecant x, then we can use the substitutions recommended in section 7.2. Rational functions. If f is a rational function, we use the procedure of section 7.4 involving partial fractions. Integration by parts. If f of x is a product of a power of x or a polynomial and a transcendental function, such as a trigonometric, exponential, or logarithmic function, then we try integration by parts, choosing u and dv according to the advice given in section 7.1. If you look at the functions in exercises 7.1, you will see that most of them are the type just described. Radicals. Particular kinds of substitutions are recommended when certain radicals appear. Number one, if the square root of plus or minus x squared plus or minus a squared occurs, we use a trigonometric substitution according to the table in section 7.3. If the nth root of ax plus b occurs, we use the rationalizing substitution u equals the nth root of ax plus b. More generally, this sometimes works for the nth root of g of x. Number 4, try again. If the first three steps have not produced the answer, remember that there are basically only two methods of integration: substitution and parts. Try substitution. Even if no substitution is obvious, step 2, some inspiration or ingenuity or even desperation may suggest an appropriate substitution. Try parts. Although integration by parts is used most of the time on products of the form described in step 3c, it is sometimes effective on single functions. Looking at section 7.1, we see that it works on the inverse tangent of x, the inverse sine of x, and the natural log of x, and these are all inverse functions. Manipulate the integrand. Algebraic manipulations, perhaps rationalizing the denominator or using trigonometric identities, may be useful in transforming the integral into an easier form. These manipulations may be more substantial than in step 1 and may involve some ingenuity. Here is an example. The integral of dx over 1 minus cosine x equals the integral of 1 over 1 minus cosine x times 1 plus cosine x over 1 plus cosine x dx equals the integral of 1 plus cosine x over 1 minus cosine squared x dx equals the integral of 1 plus cosine x over sine squared x dx equals the integral of open cosecant squared x plus cosine x over sine squared x close dx. Relate the problem to previous problems. When you have built up some experience in integration, you'll be able to use a method on a given integral that is similar to the method you have already used on a previous integral. Or you may even be able to express the given integral in terms of a previous one. For instance, the integral of tangent squared x secant x dx is a challenging integral. But if we make use of the identity tangent squared x equals secant squared x minus 1, we can write the integral of tangent squared x secant x dx equals the integral of secant cubed x dx minus the integral of secant x dx. And if the integral of secant cubed x dx has previously been evaluated, see example 7.2.8, then that calculation can be used in the present problem. Use several methods. Sometimes 2 or 3 methods are required to evaluate an integral. The evaluation could involve several successive substitutions of different types, or it might combine integration by parts with one or more substitutions. In the following examples, we indicate a method of attack, but do not fully work out the integral.